So, good morning everyone. So, today we are going to look at monotone circuit lower bounds. Okay. So, in fact, as I said last time that most part of the remaining course will be focused on lower bounds now. So, this is the first lower bound that we will see. So, what we will be proving is that in the next couple of lectures is that the Clique function, okay, so the Clique function requires exponential sized monotone circuits. It cannot be computed by sub exponential sized monotone circuit. Okay. So, let me lay the framework first. So, just to formalize what we mean by a monotone function. So, I think I mentioned this informally, but let me define this formally. So, a function f is I think I need a notation. Okay, is said to be monotone if for all x comma y which satisfies the property that is 1, then the ith bit in y is 1. Implies that f of x is less than f of y. Okay. So, this is also denoted. So, there is a notation for this. So, I would have written this separately. So, this property over here okay. So, this is also denoted as, let us say we will use the notation x okay. So, essentially what this is saying is if you want to picture this, that if you look at the Boolean hypercube okay, on n variables, and now if you move along an edge of the Boolean hypercube okay, in the well where x is increasing okay. So, then the value of fx also has to increase okay. So, if you move along the Boolean hypercube, it means that I am going from x to something that is, I mean, that has, so basically if I am going from let us say x to y, so all the bit positions that are 1 in x must be 1 in y. Y can have some more ones as well, but it must be 1, and if that happens, then fx must be f of y must be greater than or equal to f of x okay. So, again another way of saying for all I, yeah, yeah, for all I. So, again, so another way to look at it is that if you look at any path okay, so look at the Boolean hypercube, look at the node the vertex all zeros and look at the vertex all ones, and now consider any path in this hypercube from the all 0 vertex to the all 1 vertex. So, this is of course a path of length n. Now, the value of fx will, once it becomes 1 along this path, it remains 1, okay, for all the points along this path, and this is true for each and every path in this hypercube. That is another way of looking at this, and if this happens, then the function is called monotone. Okay. So, now what is the connection between monotone functions and monotone circuits? So, again if you look at a monotone circuit, it always computes a monotone function. Okay. So, again monotone circuits are circuits with just AND and OR gates. The reason is because you do not have NOT gate. So, once output becomes 1, okay, it remains 1, okay, it does not get flipped back to 0. But the other direction is also true, that if you have a monotone function, then it can be computed by a monotone circuit. So, I will leave that as an exercise. So, monotone functions can be computed by monotone circuit. So, this is again not very difficult, it is just kind of looking at the Boolean hypercube and look at the Boolean hypercube of the function, and now you have to design a circuit, okay, which would accept the function corresponding to that hypercube. Okay. If you think about it, it is just a couple of lines proof, but yeah. But again the important thing is that not all functions will have monotone circuits. For example, the parity function. Okay. So, we have, I think I did mention this earlier, parity function does not have monotone circuits, it is not a monotone function, and there are other simple functions as well. Okay. So, what we are going, so let us look at one example. So, this as I was saying, this we will look at monotone lower bound for the Clique function. So, the Clique problem, okay, is a monotone function. Okay. So, why is it monotone? So, the intuitive way to look at it is that once a graph has a clique of a certain size, now if you keep on adding edges to the graph, that clique does not change, it will still have clique of that size. Okay. So, can you name some other natural problems maybe on graphs or anything that are monotone? Exactly. So, connectivity is also a monotone function, okay, because if there is a path from S to T, now if you keep on adding edges, connectivity is not disturbed. Okay. Similarly, perfect matching is also another very important candidate problem. Okay. So, let us, yeah. So, the first thing that we will see is the formal definition of this Clique function. So, this is a function on n choose 2 bits. So, basically this will basically be the function on n vertex graph, so which have a clique of size k. Okay. So, the given, let us say, the adjacency matrix of an n vertex graph G clique of G equal to 1 if G has a clique of size k and it is equal to 0 otherwise. So, clique is again a complete graph on k vertices. Okay, so this is the formal definition of the problem, and why can we assume that the adjacency matrix can be represented using a string of length n choose 2? Because I mean any graph can be represented in terms of any graph on n vertices can be represented in terms of the edges that it contains, right. There are total of n choose 2 possible edges. So, you can look at this string and wherever you have an edge you put a 1, wherever you do not have an edge you put a 0. Okay, so, that is the standard way of representing a graph as a Boolean string. Okay. And we are looking at the clique problem, we are only looking at undirected graphs over here. Huh? What are you saying? Yeah, I mean direction does not make any difference here. I mean it is a clique problem, so you are interested in finding a clique. So, a complete graph on k vertices. And again for the remaining part of this discussion, that is today and as long as we are discussing this problem, so n is fixed for us. So, whatever we are proving for a fixed n, okay, because this is a non-uniform bound. So, again, so n is arbitrary but fixed, so it will hold for all n's. Okay, so now this is the clique problem. So now I think I can define the theorem that we will prove. So, this theorem was shown by Razborov in 85 and also it was improved by Allen and Bopana, I think 85 or 86, sometime around that same time, as follows. So, there exists an epsilon greater than 0 such that for all k at most, we will keep this as n to the power 1/4. Clique k of n does not have monotone circuits of size less than n to the power epsilon root k. Okay. So, by this exercise, of course, clique has some monotone circuit, okay, but what this theorem proves is that the only monotone circuit that it will have exponential size. Okay, it does not have sub exponential sized monotone circuits. And the only condition here that we have is that this is for k at most n to the power 1/4, but that is still large enough. I mean n to the power 1/4 is still a polynomial in n. Okay. So, how do we go about proving this result? Okay. So, what we will show is, let me give a very brief overview of how we would go about showing this. So, we have this circuit consisting of AND and OR gates. Okay. So, first we will show that clique does not have a good approximation circuit. Okay. So, we will call it as a approximator. Okay. So, the first thing that we will show is clique Kn does not have good approximator circuits. Okay, fine. And given approximations to the inputs of an AND or gate, we can compute, let us say, given good approximation. So, given good approximations to this, we can compute good approximation to the or of the output. Okay. So, these two kind of would imply that therefore, we need large size circuits for even to approximate clique. Yeah, so the second condition, what it is saying is that, so we will be defining what we mean by our notion of approximation, we will define what we mean by good approximation, we will quantify all these terminologies. But essentially what the second condition is saying here is that, well, if you have these AND and OR gates, and if you assume that the input to these AND and OR gates have good approximations, okay, so these they are free, I mean these wires have good approximation, then we can construct a good approximation to these AND and OR gates as well. Okay, and we will see today that what we mean by.
In order to get the final conclusion, we have to show that we can only compute the approximation if and only if we have good approximation for the inputs, right? Otherwise,
If and, what do you mean by if and we can say that again?
Compute the approximation if and only if we have the approximation for the inputs to the AND and OR gate.
No, that does not say much. Okay, so yeah, so only if you have approximation to the input you get the output, and well, the other direction is not clear. I mean, if you have a good approximation to the output gate, that does not mean you will have good approximation for the input. So, it is one direction, but one direction is good enough for us, that given good approximation to the input gates, you need good you will get good approximation for the output gate. That is good enough for us. Okay.
But if it is like we can, even without good approximation for the AND and OR gate, there is some other way to get good approximation for the output gate. Is it possible? I mean,
that might be possible. Yeah, that is absolutely.
How is the conclusion that we can't do the approximation?
No, the conclusion actually follows from this, the first condition as well, that clique will not have good approximation circuits. Okay. So, what we are showing here is that monotone circuits, these AND and OR gates can be well approximated, but the clique problem will not have good approximation. We will combine both these two, and then these two kind of imply that therefore, the only way in which we can get a circuit for clique is if it is a large circuit. Okay. So, when I say clique does not have good approximation circuit, I mean that small good approximation circuits. Okay. So, we will have a bound. Yeah, even the first one will need monotone, yeah, I mean the fact that it is a monotone circuit. Okay, so let us see. So, next let me define this indicator function, the clique indicator function. So, for every S, so think of S as a subset of the vertices. Okay, so for every S subset of N, define the clique indicator function Cs. Okay, so this is again a function from which takes a graph as input and it outputs a binary value as, so CS of G is equal to 1 if the vertices S in G forms a clique, okay, and it is equal to 0 otherwise. Okay. So, fix some set. Okay. So, this is basically indexed by. So, again here we are using the convention that the vertices of G are labeled from 1 to n, okay, because only then it makes sense to talk about if the vertices S, because S is just a subset of 1 to n. I mean, yeah, S is just a subset of 1 to n. So, for any such set S, okay, so basically for all the graphs for which those sets form a clique, I will output 1, otherwise I output 0. And now I can define, okay, so now we can define the clique function in terms of these. So, what would be the clique function in terms of these indicators?
Or over all subsets of size.
Exactly. So, or over all S such that size of S is k of CS. Okay. This is for G. So, clique of G is equal to or of this for CS of G. So, the just keep one thing in mind over here, that how large is this OR. Okay. So, this OR is of size n choose k, right. So, n choose k is of the size of n to the power k roughly. Okay. So, this is basically quite a large OR. Okay. So, we will try to, so our approximator, I am going to define the approximator very soon, will basically be an OR of a small number of indicator functions. So, here I have an OR of at most n to the power k, but we will show that we can bound it by a smaller number. Okay. So, what we mean by approximator circuit? So, an approximator circuit is either 0 or 1 or it is an OR of at most m clique indicators each over sets of size at most L, size at most L. Okay. So, our m will be this value, okay, p minus 1 raised to the power L times L factorial. So, note that here we have two parameters. Okay. So, this definition is using two parameters. One is of course L and the other parameter is P. Okay. So, m is defined in terms of P and L. So, m depends on this, but there is this other parameter P. So, P and L are, let me write the bound on them. So, P greater than 2 and L greater than 2 are parameters whose value will be fixed later. Okay. So, P and L will depend on K and N. Okay. So, note that we are given K and N as input. So, right now we will just take P and L to be some arbitrary parameter, later on we will fix their values. Okay. So, just the point to be observed here is that an approximator circuit, as I said, it can either be the constant 0 or 1, or it is an OR of, it is a disjunction of at most m clique indicators. Okay. So, this is what I was saying is the bound. So, this we will see that this m is not very large, it is actually, we will keep that as small, and each of these clique indicators are over a set of size at most L. Okay. So, here note that when I say clique indicator over a set, I am referring to this set. Okay. So, this set here has size k, but what we are saying is that the sets, these sets will have size at most L. Okay. So, again we will see what these values are. Different sets can have different sizes, yeah, just at most L.